as the question says, figure shows a rough track, a portion of which is in the form of cylinder of radius r. With what minimum linear speed should a sphere of radius r be set rolling on the horizontal part so that it completely goes round the circle on the cylindrical part? So we need to throw this ball with a velocity v so that it covers whole of this circle. Now we all are knowing that if it is able to cross this topmost point, then it will be able to complete the circle. This we have done in the chapter, the circular motion, right? So we need to frame the conditions such that it is able to cross this topmost part. Now when this is at the topmost part, then if we assume the radius of this small block to be small r, then I can write down that the centripetal force mv square by r. Now what is the r from the center? This is capital R minus small r, because we will be taking the center of mass of the ball, small r, equals to mg, which is the total vertical force, that is mg. We are taking the normal reaction to be 0 because we need to find the minimum velocity. So this is the case. Let us take it as equation number 1. Now if this ball is being thrown with a velocity of v and it will be having a rotation motion over it like this, so there will be no friction acting over the block, that is the ball. So we can also employ the conservation of energy over here between the initial and the topmost position, for which we can write it out as the initial velocity being half m v dash square, that is if we take this to be the v dash velocity, right, equals to, plus there will be some rotational energy, that is half I omega square equals to mg square into r minus r plus half mv square plus half I omega square. Now why we have taken this half I omega square into consideration while at the initial position there will be no omega, is because when there will be no omega, there will be some friction acting over it, right? So we are considering when this is v dash velocity and it is rotating with a angular velocity omega, so that no friction acts over it. That is why we have taken this rotational energy as well. And now when it reaches the topmost point, we need to find the v dash minimum. So this is a general equation, but for v dash minimum, we can take the omega to be 0, making this last term to be 0. And why we could take omega equal to 0 is that this is the limiting case when it stops rotating over here and it is just at, and it will get down over here. It will then therefore increasingly obtain some omega while completing the circular motion, but we have taken the limiting case when omega is equals to 0. Now putting the value, that is I is 2 by 5 mr square, because it is a solid sphere. So we can get it as 7 by 10 mv dash square equals to g square into r minus r plus 7 by 10 v square. Now putting the value of v square from equation number 1 into this equation number 2, we can get the v dash square equals to 27 by 7 g capital R minus small r, giving us the v dash minimum to be under root 27 by 7 g into r minus r.